All right, welcome to the extra credit lecture where we're going to be talking about the Morino formulation. The Morino formulation never ceases to blow my mind. It's named after a guy named Luigi Morino. He's kind of the father of panel methods. You'll find his name all over the literature. Anyway, genius guy. This formulation is a Dirichlet formulation. It includes sources though, which is different from what we've looked at before. And it includes sources in a really powerful way. Okay, so let's dive into it. As usual, what we want to do is enforce the zero normal flow boundary condition. Okay, so given some configuration, we want to say that V dotted with N is equal to 0, which, again, in terms of total potential, we can write that as partial phi partial n is equal to 0. Okay? Now, let's write that out a little bit. We can take the gradient, we can express that as the gradient of the free stream potential plus the outer perturbation potential dotted with n is equal to 0. Rearranging this, or distributing both the gradient and the dot product through, we get that V infinity dotted with n plus grad phi dotted with n is equal to 0. We're then going to take and write this term in terms of a partial derivative, and we get V infinity dotted with n plus partial phi partial n is equal to 0. Okay? Now, in terms of sources and doublets, what does this term look like? This term is half of what determines our source strengths. If you remember, we said that our source strength sigma is equal to partial phi partial n minus partial phi I partial n. Okay, so we've got half of this here in the equation, but we don't really know what partial phi I partial n is. Otherwise, we could probably express this term over here in yellow in terms of source strength. Well, let's do that actually, and let's make a choice. So these formulations are all about making different choices, and because of the choices we make, we get to different spots. As one great man once said, decisions determine destiny. So we're going to make some decisions. We are going to say that phi I, our inner perturbation potential, is identically 0 everywhere. Okay, we're just going to say I want that to be the case. And in that case, this goes away. Because if phi sub I is 0, well then its partial derivative in the normal direction is just going to be 0. And we have that sigma is equal to partial phi partial n, which is exactly what we have in our equation over here on the right. So we can write V infinity dotted with n plus sigma is equal to 0. Rearranging that, we arrive at the remarkable and non-intuitive result, I don't know, maybe this is intuitive for you guys, that sigma is equal to negative V infinity dotted with n. Now this is really powerful because due to the choices we've made, our source strengths are now only a function of local panel geometry and the free stream. We don't have to formulate a system of equations to find out what sigma is. We know sigma explicitly only as a function of geometry and free stream. And we know this independent of all other sigmas. If I want to calculate the sigma on panel I, then that is totally independent of the sigma on panel J. You know, this is an order n operation. We can loop through each panel and we can figure out what sigma is for each panel. And we do just that. Now, I'm hoping that you're saying, well, this begs the question, how on earth do you enforce this condition that phi sub I is identically 0 everywhere? Because again, we just made a choice, and this is kind of arbitrary. How do we know that that's the case? Well, we're going to force it to be the case. And what do we still have left to deal with? We still have doublets left. We haven't specified our doublet strengths, we've only specified our source strengths. So we are going to find our doublet strengths that will make this true. Okay. Now let's look at that, because our inner potential phi I is going to be equal to, well, I guess I should say phi I at some point r is equal to the sum from I equals 1 to n. We're going to sum over some panels, and I'll do this actually in terms of J, because that will make more sense with our matrix equation later. It will be the sum of doublet and source induced potentials. Now remember, the Laplace equation that we're solving here is linear, so we can take, if we have a combined source and doublet panel, we can just calculate the source influence, we can calculate the doublet influence, and then we can overlay those. It's the superposition principle, which works because, again, our governing PDE is linear. So this is then a set of source-induced potentials, so phi, or sigma sub j times phi s, I'll call that the source-induced potential, at point R, plus mu j times our doublet-induced potentials at point R. Okay, and these are the potentials induced by panel J. And we're going to say that everywhere we want that to be equal to 0. Well, let's look at this. What do we know? What do we not know? We know sigma. We know this phi here. We can calculate that analytically, and that's in the project description. And we know induced doublet potential. We did that for the last one. What we don't know is mu j. That's our unknown here. So let's rearrange things. Let's gather our knowns and our unknowns. And we will go ahead and write this as sum from j equals 1 to n of phi dj r of r times mu j is equal to negative sum from j equals 1 to n of phi sj r times sigma j. Okay? And again, looking at our knowns and our unknowns, everything over here is known. And we know this. Now, we just don't know this. So, what do we have to do? Well, we need to create a system of equations. Again, we have n unknowns, so let's create n equations. Just like we did with the previous Dirichlet formulation. Remember, the Morino formulation is a Dirichlet formulation. We're going to take and place a whole bunch of points inside our configuration. Again, we will do that based on knowing what the normal vector to each panel is. We'll trace that back from the centroid, and we'll place a control point with some offset distance L. Okay? Then at each one of these n control points, we'll go ahead and enforce this equation. And we can thereby build up a linear system of equations, where we have on the left-hand side our known doublet influences, our unknown doublet strengths, and then on the right-hand side we have our known source influences and strengths. Because what we're doing is we're saying, okay, we know what source strengths are, and so each one of these control points, we know what perturbation potential is being induced by our source panels. And we want to figure out what are the doublet strengths that will cancel out those induced potentials. Because again, we want this condition here that our inner potential is everywhere 0. So we want to find our strengths, calculate their influences at each one of the control points, and then figure out the doublet strengths that will cancel out those influences, that will make it so that the inner potential is everywhere 0. So this will turn into a matrix equation of the form we will have phi, oh dear, phi d okay, phi d from panel J on control point, or sorry, 1, 1, phi d from panel 2 on control point 1, so on and so forth, phi d from panel n on control point 1, that gets multiplied by our vector of unknown doublet strength, and that in the end has to equal on the right hand side the negative, oh dear, I hate it when this happens. And I'm going to run out of room here. Zoom out a little bit. There we go. This in the end will equal the negative of the sum from J equals 1 to n of our source-induced potentials on panel 1, on control point 1. And then the next term will be from J equals 1 to n of our source-induced potentials on control point 2. So on and so forth, all the way down to control point n. Okay? And these rows over here get repeated for each control point. So this method is a little more complex than the previous Dirichlet formulation we looked at, and we would expect that from the fact that we're now calculating source influences. But it works really well. The Morino formulation is extremely popular, especially back in the day when panel methods first started coming out. So we can solve this. We've taken that arbitrary constant on the inner potential into account, we baked it into our equations, and so this set of equations is well posed, and we can get out our unknown doublet strengths. Now, you still need to calculate the gradient of your doublet strength, the same as before, but we're going to use it slightly differently, because previously we had that our total inner potential was equal to some constant. And that led us to the conclusion that the velocity on the surface is equal to the gradient of mu. Okay, that's what we had before with the Neumann formulation and with our previous Dirichlet formulation. This is what we have. This is not what we have this time. Okay, remember that. Let's just go ahead and do this from the beginning. V on the surface is equal to the gradient of the total potential on the surface, which is equal to the gradient of free stream velocity plus mu. Now hold on a second, I'm forgetting. So the difference here is that we need take into account sources. Because we have sources on the surface, those induce a jump in the normal vector, or sorry, a jump in the normal derivative of velocity potential. And this we need to look in terms of, we need to look in terms of perturbation potential. So V on the surface, and let's remember, and this will make our life a little bit easier, let's remember that we've already said Vn on the surface, or V dotted with n on the surface is equal to 0. That's our zero normal flow boundary condition that we've enforced. Okay, so just remember that. And because of that, I can say, and I can kind of ignore sources here, that on the surface of this configuration, our velocity is going to be equal to the gradient of the free stream potential plus the perturbation potential on the surface. Well, the perturbation potential on the inside we've said is 0. That's the condition we wanted to enforce. And then the jump going from the inside to the outside is equal to our doublet strength. So on the surface is again just equal to the doublet strength. And so this then gives us the condition that this is equal to the gradient of phi infinity plus, phi infinity plus mu. We can distribute the gradient through. We can say this is equal to V infinity plus grad mu. Okay? So this now is what you're going to be using to calculate your surface velocities. Like I say, you calculate your gradient of doublet strength exactly the same, but you use it in a slightly different way to calculate your surface velocities. So, to get your surface velocities, use this equation, and once you've got that, you can use that to calculate forces, or pressures and forces the same as you did before. Okay, notice that sources don't come into this relation here, which may seem a little odd, but that's simply because we've used sources to enforce this normal flow condition here. We know that that's the case, and we can kind of just ignore it in our velocity, in our surface velocity calculation. Okay, that's all I have to do today, and good luck with the